This is the cryptic world of technology, where the rules are really just suggestions. Have you ever stopped to think about the crazy thing that connects your washing machine motor, your fan, and even the massive engines that push those high-speed trains? It's one single principle, and it hasn't changed in over a century, relying entirely on one metal: copper. Copper has ruled the electric motor game for over 100 years. It's the gold standard, superconductive, meaning electricity passes through it with almost zero resistance. Then aluminum showed up, lighter and cheaper, finding its niche in certain designs where weight was the real priority. But at its core, the job has always been the same: guiding electric current through those tightly wrapped metal coils to create magnetic fields and make things move. What if I told you that century-old principle has been absolutely shattered? What if I told you there's a new motor out there with not a single gram of metal? No copper, no aluminum, nothing. A motor that, frankly, shouldn't exist. Yet it spins, it works, and it promises to change everything we know about motion itself. How can a motor work without metal wires for real? What is this magic material that's replaced the king, copper? And more importantly, what is our future going to look like when motors are so light and flexible they can literally be woven into our clothes or the skin of robots? That's what we're diving into in today's episode. Deep inside a research lab at the Korea Institute of Science and Technology, or KIST, a small group of engineers started asking the question no one had dared to ask. What if electric motors didn't need metal coils at all? This wasn't just a casual thought experiment. They knew the challenges. Metals weren't chosen by accident. They were chosen for three reasons: reliability, conductivity, and easy availability. But the KIST team thought there was room for something much better, something lighter, something fundamentally different. Their focus shifted to carbon. Not the dull gray graphite you find in a pencil. No, this was carbon on a nanoscale. Imagine tubes made of pure carbon atoms, each one tens of thousands of times thinner than a human hair, yet somehow stronger and more conductive than most of the materials we use today. These are carbon nanotubes. The next challenge was immense. How do you organize them so electricity can flow smoothly just as it does through a solid copper wire? And this is where their real breakthrough happened. They came up with a process with a complicated name: Lyotropic Liquid Crystal Assisted Surface Texturing, or LAST for short. But the idea, though, is simple and beautiful. They aligned millions of these nanotubes into one unified, flexible cable. They called this wild new material CCEC, or Core Sheath Electric Cable. Unlike traditional wires, this thing wasn't rigid. It could bend, twist, and even stretch without losing its ability to conduct electricity. For the first time, these researchers were holding a cable with no metal in it, but that behaved exactly like metal. And when they built a motor with it, something truly unbelievable happened. It worked. At first glance, it looks like a complete magic trick. How can a motor generate motion without metal wires carrying the current? But when you dig into the science, it starts to make sense. In a conventional motor, the copper coils carry an electric current. That current creates a magnetic field that interacts with permanent magnets or other coils, making the rotor spin. It's a simple yet powerful process. With these new carbon-based coils, the core physics haven't changed. Electricity still flows, magnetic fields still form, and movement still happens. What's different is the path the electrons take. Inside the CCEC cable, those millions of nanotubes run parallel to each other, aligned with microscopic precision. These nanotubes act like electron superhighways, allowing current to flow with amazing efficiency.
The researchers tuned the structure so the density and alignment of the nanotubes essentially mimicked the behavior of metallic conductors. A protective sheath surrounds this core, giving the cable both flexibility and rugged durability. Unlike copper wires that risk breaking when repeatedly bent, this carbon cable can twist and flex without damage. And when they wound it into coils and placed it inside the motor casing, these carbon cables responded just like copper does. Apply a current, the magnetic field gets to work, the rotor spins, the motor runs, but now it does so with dramatically less weight and with materials that can bend and stretch in ways no traditional motor ever could. What started as a risky materials science experiment turned into a working, spinning, electricity-fed reality. Once the motor started spinning, the true magnitude of the breakthrough became absolutely clear. This wasn't just about making something work, it was about making something better in almost every important way. First came the massive weight reduction. The motor saw a weight drop of over 80%. Copper is dense and heavy, and in industries like aerospace, automotive, and wearable tech, every extra gram is the enemy. This reduction is not a small upgrade, it's a total design leap, opening up new possibilities for range and endurance. The second key benefit is the flexibility and conformability, which allows for the possibility of integrating motors into fabrics and soft robotics. Traditional motors are rigid and bulky, but the carbon coils allow the motor to bend, compress, and twist without losing performance. Imagine robots that move with actual muscles instead of stiff, mechanical joints. Plus, there's an efficiency boost, with tests showing conductivity improved by over 130%. The organized nanoscale structure minimizes energy lost as heat, converting more of it into useful motion. On top of that, the lower mass means faster responding and generally more agile motors. This innovation means longer range for electric vehicles with smaller batteries, it means extended flight times for drones, and for wearable medical devices, it means lighter, more form-fitting designs you'll barely notice. This development is forcing engineers to ask, what is the new limit for motion? For every breakthrough, there's always a reality check, and the carbon-based motor tech is no exception. The first major hurdle is the high manufacturing cost. Producing carbon nanotubes at the required purity and precision is still incredibly expensive compared to cheap copper and aluminum. Then there's the conductivity gap. Despite the excellent performance in high-performance, large-scale motors where there's no room to increase volume, the conductivity still cannot absolutely match copper yet. Finally, there are durability and environmental concerns. Carbon nanotubes are susceptible to oxidation and moisture. Working with nanomaterials also raises serious questions about long-term environmental and health safety standards, research that is still ongoing to address them. So why aren't companies talking about it? Simply put, it's stuck in the transition phase. It's too advanced, too expensive, and still under highly secretive testing by the major players. Defense contractors, aerospace engineers, and advanced robotics firms are watching it closely, but none of them are keen to show their hand just yet. Electric motors have spoken the language of metal for 100 years. Now, in a quiet corner of the world, carbon is rewriting the very rules of motion. This is a journey that will take time to move from the lab bench to the factory floor. But when it happens, you'll know. Because your next motor won't hum with copper, it'll buzz with carbon.